Alright, as we're taking a look at the next section, time value of money, we're finally going to get into some calculations here where we're talking about how money grows over time. And in the materials you have this example here. Here, I'll cover up some stuff and get you out here. You have an example of what's happening with some money. Going in increments of 5 years, it starts off being worth $2,600 and ends up being worth $9,062. So if you remember all your old skills for math and you went and put that in the stat menu, so stat edit, you enter all that data, and then you try to take a look at the scatter plot, you see that it curves up. And what we're looking for is this regression equation that goes through it. So stat edit, we do the exponential regression equation, and we get the equation out. So 2,600 is the starting amount, and I'll try to shoot over here so you can see the number in parentheses, 1.0425. So what does that tell us? Okay, if this is the regression equation, I can be able to pull out the interest rate if I know how to interpret what is in here. So because you're increasing, it's 100% plus the new amount, that 0.0425 tells you that the interest rate is 4.25%. And then they might ask you to use it. So it's growing exponentially, it's growing faster over time, and I can figure out the interest rate by doing the regression equation and looking at that base, but they might ask us to use it and say how much is in there in 50 years, so that's where you want the calculator to come into play. If you have the equation in, go to year 50, and 20,834 would be what that money grew to. So first of all, think about that. You start off with 2,600, at 4.25%. In 50 years it grew to be 20,000. So this is the amount, 20,834, it is worth after that length of time. Now hopefully this will refresh your memory. When we get down to problem 8 and 9, it says to use basically the old formula that you use all through middle school and in previous math classes. You have a present value, you have a future value, but sometimes things aren't compounded just annually. Sometimes they're compounded quarterly, 4 times a year. Sometimes it's compounded monthly, 12 times a year. And what that does in the formula is it puts the number of compounding periods in both the exponent and underneath whatever the interest rate is. So question 8 says if you invest 2,600 at 4.25% compounded quarterly, so that's not once a year, that's 4 times a year, what would your balance be in 5 years? So let me pull the calculator up so you can see this. You're taking the initial balance, this is present value, 0.0425, you have to convert that percent into a decimal, and the 4 that's here is for quarterly, the 5 is for 5 years. So if I figure out what that is, I end up with the amount after 5 years, and if you want to do 50 years, I'm going to pull that back up and just go and change my number of years to be 50. Oop, gotta slide that up a little higher there. There we go. Change that to be 50, and your money will have grown to this. So in questions 8 and 9, they're asking what your money has grown to. So right here you see 3,000 to 1199, and then this is changing the year to be a 50 for number 9, and this is 21,526.87. So both those rounded up with the pennies. Alright, and now we need to have some fun, so it's joke time! Yay! So my question is, what flowers grow under your nose? What flowers grow under your nose? Do you get it? Do you get it? What are those? Tulips! Alright, that is one of your answers to fill in, but now let's move on. I want to start looking at what you need to do with your calculator pretty soon, so please make sure you have your calculators with you for all this. I want to ask you, what would you do with $1 million? Think about that, because that's what we're looking at today. So as you think about that, we are going to look at kind of the table that we had in the last example, but flipped around. So if you let your money sit for 30 years, yes, it will grow to be a certain amount of money. That means think about how old you might be now. Maybe you're 18 years old now. If you sock that money away, in 30 years, it will grow here. So if you wait till age 48, you're going to have to put that much money in. If you wait 10 years, so you're 28 years old, you'll only have 20 years for that money to grow. So you'll put in more than you would now, but less than if you waited. So this is the part of the unit where it starts talking about don't wait to retire until you're in your 30s or 40s. Like, it's expensive then. So Josephine is our first person. So she's 20 years old. She wants to save $1 million for retirement in 50 years. Assume she invests in a savings account that earns at least the current rate of inflation. Well, in 2020, that's all over the place, so we're just going to make up a number for today. Determine how much Josephine must save today to reach her retirement goal. And we're going to use the regular old formula. So present value, future value, this is the number of compounding periods per year, and I is the interest rate in decimal form. So I kind of have this filled out. I thought this would be helpful to see it all. This is just the same words from the other page. I'm just going to have us use 2.5% in the first chart, and I want you to think about what's happening. If she's 20 now, she wants to retire in 50 years. So I'm just making up those numbers. It could be 18 and 68. But I did 20 years old, 70 is when we're going to retire. There's my 50 years. Well, if she waits till age 50, she's going to have $1 million in there. But if she puts the money in now, and we're using, I made up the 2.5% here, if she had 50 years for the money to grow, she could put 50 in her exponent. Now, why did I divide it? You have to think about this. We're solving for present value. So you have $1 million on the left side, and you have to divide this stuff over. So here on the calculator, you see 1.025, that's 2.5% interest for 50 years. So if she put away $290,000 now, not that it's normal to have that laying around, but if she put that away now, it would grow to be $1 million. I will do the next row here. If she waits until she's 30, she would only have 40 years for that money to grow. So she would have to put in more, and she would have to put in $372,000. If she waited till she was 40 years old, it would only have 30 years to grow. So what I'm putting in the calculator is matching this little pink number over here. So if the money had 30 years to grow at 2.5% interest, she would have to put in $476,000. But I want you to think about something. What if you found a better interest rate? What if your adjustment was, instead of going from 2.5%, what if you found something that was growing at 5%? So same thing, at age 40, I would still have 30 years for the money to grow, but my interest rate would change. See if I can just delete that 2 out there. And she would have to put in less. So I want you to think about this. At age 20, if she let that money sit for 50 years, this would be the amount she would have to put away in order for it to grow to be $1 million. If the change was going from 2.5% to 5%, she could put in less than that at age 40. So at 5% at age 40, she could put in $231,377.45. If you're following along the notes, that number and that number on your Google form you're filling in are very important. Alright guys, and then there is Blaine. I pretty much just took shots of people so we would have something to look at here. But Blaine wants to have $1,000 in 10 years. Not a very big goal, just something little. And the following are choices in which he can invest. So a savings account earning 3.8% compounded quarterly. How much money would he have to put in now at 3% compounded quarterly, that's where the 4 comes in, over 10 years for it to grow to be 1,000? So if I pull my calculator up here, this is what I have in turquoise. I have it typed in here. He would need to put in now $741.65 to have that money grow to be $1,000. That's the savings account. The next is the checking. A checking account is another option he has. It earns only 1%, but it's compounded monthly, so more frequently. Here's purple. All right, so he's trying to figure out how much to put in now. If it grows at 1%, monthly means we put 12s in, still for 10 years. So purple, this is what I have loaded into the calculator now, and he would have to put in more, $904.88. So the last option he has is this thing called a money market account. It earns 4.5%. It's compounded semi-annually. That's twice a year. So 4.5 is the highest percentage so far. That's a good thing. And I'm trying to do this final calculation now. So I have the 2 in for semi-annual, I have the 4.5% in, so that would mean he would only have to put in $640.82. Now I want you to think about this. These are 3 different options for him to grow to $1,000. Would you rather put in 741, 904, or 640? So would you rather do the savings, the checkings, or the money market? And unless you're crazy, you'd like the bank to grow for you, so this is your answer. This is what you would advise Blaine to do.